Hello everybody. In this video, it is related on the linear algebra course, uh, Maths2501, Maths2099 at University of New South Wales, or any linear algebra related with the definition of the determinant in general form. So that's the explanation of the formula, explanation of the what's the determinant. Okay, now if you have for every n by n square matrices, if the determinant is not equal to 0, this is if and only if there exists an A inverse. A inverse means in an invertible matrix, A times A inverse is equal to A inverse. A is equal to identity. So this is just a reminding ourselves what we talked about before. So this is why I am not looking at the details for this part. Now we would like to calculate the determinant. Determinant gives you a number related to the matrix. And the calculation of a determinant is recursive formula in a recursive way. So the determinant of a 2 by 2 matrix is basically the main diagonal minus the other ones, as we know before. Now, if you have a 3 by 3 matrices, then you can calculate any row with respect to any row in a column. You are going to write it down a series of the 2 by 2 matrices, and that will allow you to calculate the 3 by 3 determinant. So that's the idea. Now, before calculating or giving a general definition of a determinant, we need to understand what does a minor means of a given A by A matrix. For example, if you have A matrix is n by n, then you obtain n minus 1, n minus 1 matrix. Obtain it by removing the ith row of jth column. The left of the matrix will give you the minor of it. So the minor of AJ will be the removing the ith row and jth column, and whatever it's left will be the one less degree square matrix. For example, if you have a 3 by 3 matrix of this form, if you would like to look at the A23, the minor A23 means that you're removing the second row, third column. This is how you obtain this matrix. This is A11, A12, A31, A32 will be this matrix. So the minor of minor A23 is this matrix. We are going to use in the definition of determinant formula. Determinant formula for any row I, right? You're focusing on one I, any I. So for example, if you think that you're focusing on the first row, then this will be the 1 plus 1, A11, whatever that row is. And then you will have the minor when removing that. And then you will have minus 1, 1i plus 2, ai2, aii. This is the minor, and you will calculate the determinant of that minor. And the minus 1, the ith row plus 3, ai3, a13. So that's the minor related to it. So you will focus on either one row or a column, and that will be the formula for the determinant. Okay, if you look at the jth column in a similar way, but in this case, the second component will change, right? A1j, A2j, A3j. So this is really the 3 by 3 matrices determinant. So this is the general format. Let's do the example. So for example, if you have if you want to calculate the determinant of a 2 by 2 matrix, this is the main diagonal. So 5 times 2 minus, because this is the opposite diagonal, that will be the negative. So that's minus this times this, which is minus 7. But since you have a negative here, then you will have plus 17. So plus 17 is not equal to 0. So A has an inverse. You can check it out. You can find it out. Now B. Assume that we have a 3 by 3 matrix. Right. Now now this opening up with respect to the first row. Now the first row, the 0, with respect to this one, since I will have this as a point, then this one and this one will go, and the minor will be B11 will be this matrix. Then I have -1. This is the first row, second column. This is why I have there as a power. First row, second column, 1 plus 2 appears here. And then the element here, which is 0, that is the 0 element here. Then the minor of B12, which means that you will remove this row with this column, whatever the matrix you left will be the minor B12. Now the last one here, because my focus was the first row, so I open it up, the determinant formula with respect to the first row, and this is why I got the 3 in the end. That is the 3 is here. Then this is the first row, third column. This is why I have 1 here that corresponds to first row, and this is the third column. And then if you remove the yellow part, you will find B13. This blue part is the minor B13. And that's what it is. So what I have here, this is -1 to the power 4. That's basically +1. I have 3 here. That's that 3. Now I would like to calculate this is minor, the determinant of the minor B13. Basically this times this, which will be -2. That's -2. And this times this, because this is an opposite diagonal, that will be minus times 1 times 9. So this is why I have -1 times 9. That will give me, this will be -2 minus 9. That will be -11 times 3. That will be -33, which is not equal to 0. It means there exists a B inverse. Now, there exists a quick way to calculate the determinant. By just this is a usual way. This is by using this one, by using the first row. I could use this row, I could use this column, any column and row I could use, as long as I am using these formulas correctly. I will find exactly the same number, which is a determinant. Determinant was the unique for, sorry, this one. So for this is unique. For each matrix, for each square matrix, determinant is a unique number. So whatever your rows or columns are choosing, it won't matter. You need to find exactly the same number. In 3 by 3 matrices, you have a quick way to calculate the determinant. By looking at basically the symmetries, this is what I'm talking about here. You have main diagonal, which is this one. Basically, will gives me the 0. And then I'm looking at the entries. This one times symmetric entries above with respect to the main diagonal. They will be all additions. So this times this will give me 0. And then you have 2 minus 1 and 3. You multiply this 3 number and add. So that's 2 times 3 times -1, which is this number. And then you have the opposite diagonal ones, or the opposite diagonal, and the all symmetries of the opposite diagonal ones will give you the negative. So that's the negative part. So 319 is this one. And the symmetries will be this times this times this. Think about this blue one. This will be the symmetric with respect to that one. It's like a T symmetry. 2 times 0 will give you 0. And then you have think about this one opposite diagonal one, and this one times this one and this one is like a t-symmetry with respect to this blue one, gives you the 0 as well. So this number will be minus 6 minus 27. That will give you minus 33. That's exactly the same. Okay, another way to calculate a determinant is by using the row operations. By using the row operations, you can reduce the degree 2 by 2 matrices. For example, if you have a matrix C, and then by using the row operations, you can obtain the first column as 1, 0, 0. And then you will have take the determinant formula with respect to the first column. You have only this minor will appear, which is C11 minor. You have only one entry, and this one entry is in the first row, first column. So the minus 1 to the power squared will be 1. Then only thing the minor, it will be this determinant, and that will give you the result. But not all row operations will be, some row operation changes the determinant, some row operations does not. If you have a row operations, this is the part that how the determinant is affected by the row operations. That's what I'm saying here. If you have the row operations, like adding a row, multiplying a row j with a non-multiple, and then the adding to the row I, does not affect to your determinant. So these are the same. If you swap these any two rows, it affects the determinant with -1 factor. If you have the row operation by multiplying a row by a vector, by a number alpha, then the determinant is affected by the 1 over alpha multiple of the determinant. So these are the two tools for us, and we can use those tools and simplify our matrix by using the row operations, and then calculate the determinant. Of course, we need to use the definition of the determinant formula in order to be able to calculate it. Okay, this is a very simple way because now you have only the minor of this one. So the determinant of C will be exactly the determinant of C prime because these ones will not affect. The determinants will be the same. So this is a 2 by 2 matrix here, right? This is the minor that I'm talking about is 3, 1, minus 12, minus 4, which is this guy. And the 2 by 2 matrix, so this times this minus this times this, will give you the determinant of the matrix C prime, which is exactly the matrix C. In this case, the inverse does not exist because the determinant is 0. Now, this is another example. Now, think about that you have a 4 by 4 matrix. In this case, how you calculate the determinant? Now, same trick. Apply the row operations to make the appearances of the matrix simpler, such that we can calculate the determinant in a simpler way. So if you can make these 0, 0, 0 by using the row operations. Each of these row operations, 2 times this add here, 3 times here add here, 6 times this add here will make those ones 0. And none of these operations will change the determinant. So the matrix that we obtain here by using the row operations is D prime, and the determinant of D is equal to determinant of D prime. That's what I'm saying here. But the determinant will be, again, the recursive formula. I am going to use, focusing on the first column. So this is -1, so that's -1. The entry is there. And then the position of that entry, the first row, first column, this is why I have -1 to the power 1 plus 1, first row, first column. Now this will be plus 1 and this will be the entry minus 1, and the minor of this, the minor of that 1 1 position, which means that you're removing this one, this column, and this row, and the matrix is here. This matrix will be the matrix we need to calculate the determinant on. That's the minor B11, D11, sorry, in this case. Okay, we can use the quick way of calculating this 3 by 3 matrix, which is the main diagonal, 0 times minus 1 times 21. And then you have 5 times, so that will be 0. 5 times 4 times 9, that is the symmetric positions with respect to the main diagonal. So that will give me the 180. And then you have other symmetry that is given by 6 times 1 plus 10. That's 60. Now, from this point, we are going to look only the opposite diagonal ones. All the opposite diagonal ones appear with the negative, right? So this is negative 9 times minus 1 times 10. So that will be plus 90. That's why I have plus 90. And then the symmetry with respect to the opposite diagonal, that diagonal. This 1 times 4 times 0, that's 0. Now this is opposite diagonal. The symmetry with respect to the opposite diagonal will be 5, 6, 21, but that's negative because that's the symmetry with respect to the opposite diagonal with respect to this part. So this is why I have minus 360. If we calculate this one, we will have a positive number, which is not 0. So anything which is not 0 implies that there exists an inverse. Okay. Now, let's find all the roots of the polynomial. Find all the root of the polynomial. So this will give us the polynomial because the determinant is one number, but this will be the polynomial in a sense that because we have some x's here. So from the matrix, let's call this matrix A, let's apply the row operation because you have 1, 1 here and 1, 1 here. Whatever the things that you would like to do, we can, since we have 1 here, we can make this 1, 0, this 1, 0 by doing the column operations. And the similar things are valid for the column operations as well. Our idea is just to simplify this matrix so that we can calculate the determinant easily. We can do in many ways, as I said. We could do directly from this matrix by applying the definition. We can use definition and we can do it. Or we can calculate in a quick way by looking at the symmetries. We can also this way, reduce the matrix by using the row or column row operations and calculate the determinant after in the simplified matrix. Well, since I have 1, 1, like similar numbers, I could also make this 1, 0, this 1, 0, whatever you wish, right? So if you do that, these ones will not affect the determinant. So the matrix that we got here is exactly, has the same determinant. If I open up with respect to this last row, these are 0, so that will disappear. And this one will be the only element will be left. So the position of this element is a third row, third column. This is why I have 3 plus 3 minus 1 to the power of the position numbers. That's 3 plus 3, third row, third column. And the element here is 1, that is 1. And we remove this row with this column, and the minor that we left here is 2 by 2 matrices. That is this one, which is the minor A prime 3, 3, right? This is minor A prime 3, 3. The determinant here, this times this, minus this times this. So we have this polynomial. This will give us positive 1. This is 1. So this times this minus this times this is this polynomial. organize these polynomials, then we have x minus 1, x squared plus x minus 3. And x is equal to 1 is a root, and we can also write it down this for quadratic equations as x plus 2 and x minus 2. Then you have x minus 3, x is equal to 2 are the roots of this polynomial. So the roots are minus 3, 1, and 2. Okay, now in this question, we are going to use some properties of the determinant in order to be able to simplify this thing. Okay, so we assume that there exist A and B are invertible matrices. This is what it means here. There exist A inverse, B inverse, and by n matrices. And then this determinant of this term is equal to 1. In order to be able to show that, these are the green areas. These are the facts that we know, some properties of the determinant that we can use to simplify this equation or to prove this. The first of all, if you have a determinant of a matrix A, B, then it will be determinant A times determinant B. This is the one property of the determinant. If there exists the inverse of a matrix, then determinant A inverse is equal to determinant A inverse A is identity. This is the definition of the inverse of a matrix, as we know. By taking the determinant on all sides of this equation, this will be determinant A inverse, determinant A inverse, and the determinant of the identity matrix is always 1. So that's 1. So we realize that determinant of A inverse will be 1 over the determinant. So determinant of A inverse is the determinant of A inverse. So we can see this very easily from the definition of an inverse of a matrix together with this property, we can obtain this. And similarly, determinant A transpose is equal to determinant A. This is also straightforward to find it out. Now call this left-hand side is like xi or something, and let's see how can we, what can we do with it. So this left-hand side, since this is a determinant of this, all of these multiplications of the matrices, we can separate them. We can take determinant each of them separately and multiply because of the first property that we talked about. And this one, and we can use this one. So the determinant A transpose 7, that one, B inverse 15, that one, A to the 29 is this one, B to the 11, B transpose is equal to B, that one. So A determinant A to the minus 36, this one, determinant B to the 4 is this one. Now, these are all real numbers, because determinants gives you the real number, only one number, and you can always swap them. You can always change them. Then you will be able to find all. So this is A here, A here, A here. So that will be 7 20 plus 29 minus 36, and the power of the determinant. And the determinant of B as a power will be minus 15 from this side, because I've used this inequality for B inverse 15, right? That will be the minus 15. And then the B11 here, there's a plus 11, and B4, that's a plus 4. So that will be 36 from here. This is plus 36 minus 36, so that will be 1. This is minus 15 plus 15, that's 0, that will be 1. So the multiplication 1 times 1 is 1. So that's 1. Yeah, that's all for this video. Thank you very much for watching, and hopefully this is helpful for you all. Thank you.